I want you to imagine that you are standing right at the base of this massive, jagged mountain range, and it is just pitch black.
Oh, like you can't see your hand in front of your face.
Exactly. You can't see a thing. And your singular mission here is to find the absolute lowest valley in that entire mountain range, but you're only using, the feeling of the ground beneath your boots.
Which is terrifying, honestly.
Right. You take a step, you feel a slight downward slope, so you take another step in that direction, but you are entirely blind.
Yeah, you're just feeling your way through the dark.
And you're terrified that this little dip you just found is actually, just a temporary ledge on the side of a cliff rather than the true bottom of the canyon.
The mountain analogy really captures the stress of it, but it actually misses one crucial detail about the reality of modern finance.
Oh, what's that?
The mountain you are standing on is multidimensional, and its shape is constantly shifting while you're walking on it.
Oh, wow. That is a nightmare.
Yeah, but that pitch black navigation is the exact mathematical reality that quantitative analysts face every single day. I mean, they are traversing this landscape of infinite data, searching for the mathematical minimum of risk or the maximum of return.
Well, today our deep dive is venturing right into that dark terrain. We've got a stack of source material focusing on the fundamentals of optimization and their application to portfolio selection.
Which is such a fascinating topic.
It really is. The mission here is to take this daunting, heavy mathematics used by Wall Street quants and, translate it into a logical, understandable roadmap for you.
Because it can feel like a foreign language if you aren't in the weeds of it every day.
Exactly. We are exploring how professionals actually construct portfolios. Like, how they mathematically balance that eternal struggle between greed and fear.
Right, and how they eventually have to blend cold market data with highly subjective human intuition.
So, to start, the source material lays out that every optimization problem, no matter how complex the financial derivative or, a global supply chain, it's built on three foundational pillars.
Yeah, three basic building blocks.
First, you have the objective function. This is the holy grail you are actively trying to maximize, like your overall portfolio return. Or maybe you want to minimize something like your exposure to volatility.
Right. It's the specific thing you care about most.
Then second, you have the decision variables. These are the actual levers you can pull. The specific weights to the assets you choose to buy or sell.
I like to think of them as the dials on a dashboard.
Yeah, perfect analogy. And third, you have the constraints, the unbreakable rules of the game.
And, before we even try to solve a problem with those three pillars, there are these rules for manipulating the equations to just make the computation viable.
Make it easier on the computers, basically.
Exactly. Sometimes a problem is computationally just a nightmare to solve as a maximization problem, but it's trivial as a minimization problem.
Wait, really? How does that work?
Well, the math allows us to switch between the two. Maximizing a function is mathematically identical to minimizing the negative of that function. You just have to, remember to flip the sign back at the very end.
Oh, I see. So it's like looking at a topographical map. If you simply swap the color coding so that the deepest oceans are colored like the highest peaks,
Yes.
then the mathematical process you use to find those extreme points is exactly the same. You're just searching for a different color.
That is a much better way to visualize it, yeah. And there's another critical manipulation called affine transformation.
And a fine transformation. That sounds intense.
It sounds worse than it is. It just means if you multiply your objective function by a positive constant, and then you add a baseline constant to it, it doesn't change the optimal value of your decision variables.
Okay, so going back to the map analogy, the specific coordinates on your topographical map that represent the highest peak remain exactly the same.
Exactly. You are essentially just scaling the map to fit on a smaller piece of paper or, shifting the baseline sea level to make the calculus cleaner. You haven't altered the fundamental geometry of the mountain itself.
That makes total sense. So if we are dealing with a problem that has zero constraints and unconstrained optimization, the text points us toward multivariate calculus.
Right, which brings back fond memories for anyone who took college math.
Or traumatic memories, depending on who you ask.
Yeah.
But it gives us two vital conditions we have to meet. The first is the first order or necessary condition.
The gradient.
Right. This states that the gradient, which is the vector of all the first derivatives of your function, must equal exactly 0.
So going back to navigating in the dark, a derivative simply measures the slope of the ground. If the derivative is 0, it means your foot has found a perfectly flat spot.
But a flat spot is only a necessary condition, not a sufficient one, right?
Exactly. That flat spot could be the bottom of a valley, which is your minimum, or it could be the top of a peak, representing a maximum.
For neither.
Yeah, it could just be a useless plateau on the side of the mountain, an inflection point. You take a step, it's flat, but the next step sends you plunging downward again.
So to figure out what kind of flat spot you are actually standing on, you need the second-order condition. And this involves something called the Hessian.
The Hessian matrix, yeah.
It's a matrix of the second derivatives. So it doesn't just measure the slope, it measures the curvature of the space. It tells you how the slope itself is changing as you move.
Right. So if you want to prove you have found a true minimum, your Hessian matrix must be what we call positive definite.
Positive definite, meaning what? Visually.
Geometrically, this means the space curves upward in every single direction around you. You are standing at the bottom of a bowl.
Okay, I can picture that.
And if you are looking for a maximum, the Hessian must be negative definite, meaning it curves downward in every direction. You are standing at the top of a dome.
Okay, so that sets up the abstract architecture. We have our gradients finding the flat spots and our Hessians proving whether we are in a bowl or on a dome. But we need to pull this abstract calculus down into the real world. I mean, how does a quantitative analyst actually apply this to money?
That's the billion-dollar question.
The first major application in the text focuses on balancing risk and reward through mean variance optimization.
Right, which brings us to the pioneering work of Harry Markowitz. The mean variance optimization criterion is elegant because it simplifies the chaotic market down to a few key variables.
What's the main goal there?
The core objective is to find a specific asset allocation, a vector of portfolio weights, that maximizes your expected return, subject to a mathematical penalty based entirely on the variance or the risk of those returns.
Okay, so to set the stage for this hypothetical economy, we have a certain number of risky assets. Each of these assets has an expected return and, an expected standard deviation.
Right, but assets don't exist in a vacuum, obviously. They interact, they have correlations.
Like when oil goes up, airlines might go down.
Exactly. All of this interacting risk gets bundled together into a massive matrix called the covariance matrix.
And into this economy, we introduce a very special ingredient: the risk-free asset.
Yes, the theoretical risk-free asset. Think of this as a completely safe bank account. It has a certain guaranteed return.
And because it is guaranteed, its variance is exactly 0.
Right. And because its returns never ever fluctuate, its mathematical correlation to any of the risky assets in the market is also exactly 0.
But looking at the optimization formula in the text, it subtracts a penalty for volatility from the expected return. And yet, the author explicitly calls this an unconstrained optimization problem.
Yeah, that trips a lot of people up.
I mean, how is that possible? A real investor only has 100% of their capital to allocate. That is a hard budget constraint. We can't buy infinite assets, so where did the constraint go?
It is a brilliant mathematical sleight of hand, really. The budget constraint vanishes from the equation precisely because of that risk-free asset.
Wait, how?
Well, the model defines the weight of the risk-free asset simply as whatever capital is left over after you allocate to your risky assets. Any uninvested capital automatically defaults into the risk-free bank account.
Oh, I see.
Because the system naturally absorbs the residual cash without any friction, we don't need a hard mathematical rule forcing the risky asset weights to sum to 100%. The system becomes beautifully unconstrained, allowing us to use standard calculus without hitting a wall.
That is actually really clever. And the objective formula itself is fascinating when you break it down conceptually. You start with your guaranteed risk-free rate, you add the expected excess return of your risky portfolio, and then you subtract a penalty for the volatility.
Right.
And the size of that penalty is dictated by a very specific variable, lambda. The text defines lambda as the degree of risk aversion.
Lambda is the behavioral engine of this entire mathematical model. It represents the investor's psychological tolerance for pain.
It operates perfectly as a personal fear dial.
A fear dial. I love that.
Yeah. I mean, if you are managing a pension fund for retirees, you turn that fear dial way up. Your lambda is a high number.
Right, because you can't afford massive losses.
Exactly. And when lambda is high, the mathematical penalty applied to any variance becomes massive. The optimization engine is essentially forced to dump your money into safer assets because the penalty for risk completely obliterates the potential reward in the equation.
Conversely, if you are a young, aggressive investor or maybe a venture capitalist, you turn the fear dial down to a fraction.
So the lambda is low.
Exactly. With a very low lambda, the model barely penalizes the volatility at all. The math will aggressively chase higher returns, completely ignoring the stomach-churning drops along the way because the penalty function has been muted.
And because it is unconstrained, finding the solution is straightforward. You take the derivative with respect to your weights, set it to 0, and the model reveals the optimal candidate solution.
Yep. The optimal weights end up being directly proportional to the excess returns, scaled by the inverse of the covariance matrix and, dialed up or down by your lambda.
And for mathematical rigor, we have to check the second-order condition, right?
Always. Because the covariance matrix is naturally positive definite and our risk aversion lambda is a positive number, the resulting Hessian is negative definite.
Which guarantees that we are standing at the top of the dome.
Exactly. We haven't just found a good portfolio, we have found the absolute mathematical maximum utility for that specific investor's fear level.
Before we move off the mean variance framework, I want to touch on a specific, highly technical aside in the source material regarding that covariance matrix.
The shortcut trick.
Yeah, the text outlines a shortcut for calculating it. It separates the process into 2 steps. First, you form a matrix made up exclusively of your standard deviations, so pure scale of the risk.
Right.
Second, you take your correlation matrix, which represents purely how the assets interact, and you multiply it by the standard deviation matrix.
The author makes a point to include this because it is far more than just the classroom trick. It's actually a massive deal in practice. By intentionally separating the scale of the risk from the relationships of the risk managers gain a massive computational advantage. This specific decomposition is the mathematical foundation used by platforms like Riskmetrics to calculate value at risk on a global scale.
Right, and if you're listening right now and wondering why a multi-billion-dollar bank cares about saving a few computational cycles on a Tuesday morning, it's because they are processing tens of thousands of assets.
Exactly. It's an unfathomable amount of data.
And volatility. The standard deviations, it changes wildly day to day. Correlations, however, are structural. They tend to move much slower.
Right. So by breaking the matrix apart this way, the bank can rapidly update their daily volatility estimates without having to recalculate the massive, slow-moving correlation matrix every single night.
It allows for real-time risk management that would otherwise just choke a supercomputer.
Absolutely. But, this entire mean variance optimization framework relies on a rather massive assumption.
Which is?
That we actually know what our expected returns are going to be.
Yeah, that's a big one.
If you feed bad expected returns into a Markowitz optimizer, it will flawlessly calculate the perfect portfolio for a reality that just doesn't exist.
Garbage in, garbage out. Which forces us to ask, how do we accurately predict the risk premium of an asset in the first place?
And that points us toward the capital asset pricing model, or CAPM.
Right. The core theoretical idea here is that the expected risk premium of any individual asset should be strictly proportional to the expected risk premium of the underlying overall market.
And the degree of that proportionality is governed by beta.
Beta, the famous beta. It measures the asset's exposure to systematic market risk. So if the market goes up 10% and your beta is 1.5, theory dictates your asset should go up 15%.
Exactly. The practical problem, however, is that CAPM is a forward-looking theory. But we are trapped in the present.
We don't have a crystal ball.
Right. We only have historical data. So to estimate these forward-looking parameters, quantitative analysts have to look backward.
The text provides a standard industry rule of thumb for this, doesn't it?
It does. To estimate beta, quants typically use 5 years of monthly data for established, stable companies.
But if they're analyzing a fast-changing tech company, 5 years is ancient history.
Yeah, completely useless. So they might use 2 years of weekly data instead, prioritizing recent high-frequency behavior.
And the mathematical tool they use to take that historical data and extract the beta is ordinary least squares, or OLS, linear regression.
The trusty line of best fit.
Exactly. The equation tries to find the clean slope, the beta, that best fits the messy reality of the historical data points. But it also includes an error term, which the text refers to as a disturbance term.
The error term is so important. It's the critical gap between what our elegant theory predicts should have happened and what actually occurred on, say, a given Tuesday in November.
It absorbs all the real-world friction, measurement errors, stalled price quotes, sudden news events that momentarily detach an asset from the broader market.
And for OLS to function properly, there are strict mathematical rules governing these errors. First, the mean of the errors over time must equal exactly 0.
Meaning, your model isn't systematically biased, right? Like, predicting too high or too low consistently.
Right. Second, the variance of the errors must be finite. And crucially, the covariance between different error terms must be zero.
Wait, explain that last one.
It means today's error should not mathematically predict tomorrow's error. If it does, you have what's called autocorrelation, and it means your model is fundamentally missing a key variable.
Okay, that makes sense. Now, the objective function of OLS regression is to minimize the sum of the squared errors, right?
Yeah.
You're trying to draw a line of best fit that makes the collective gap between the line and the actual data points as small as possible.
Exactly.
But this is where I want to challenge the methodology about why square the errors?
What do you mean?
Well, if my model misses the target by 2% too high on Monday and 2% too low on Tuesday, shouldn't we just take the absolute values? 2 plus 2 equals 4. Doesn't squaring them, turning a 2 into a 4, but turning a 10 into a 100, doesn't that disproportionately punish extreme outliers?
It absolutely disproportionately punishes outliers, and that is a deliberate feature, not a bug.
Oh, really?
Yes. By squaring the errors, the mathematical formula is literally programmed to fear black swan events.
Okay, walk me through that.
If you only minimize the absolute error, the optimization engine might draw a straight line that perfectly fits the mundane daily 1% fluctuations, while completely ignoring the day the asset crashed 20%. The algorithm just wouldn't care enough.
Because 20 is just 20.
Right. But by squaring the errors, a 20% miss generates 400 units of pain for the objective function. It forces the line of benefit to violently adjust, pulling it closer to reality to account for the tail risks.
Oh, wow. So it prevents the model from sitting comfortably in theory while ignoring catastrophic real-world deviations.
Exactly. And the text notes that this OLS logic scales instantly. Instead of writing out hundreds of individual equations for hundreds of days of data, you can generalize it into matrix notation.
Right, you stack all the historical data into matrices, and you can solve for multiple factors simultaneously.
You aren't limited to just comparing an asset to the overall stock market. You can run an unconstrained matrix optimization to see how an asset reacts to interest rates, oil prices, and momentum factors all at the same exact time.
It is incredibly powerful. But, we have to acknowledge a hard truth about unconstrained models, whether we're talking about OLS or mean variance optimization.
A bit of a fantasy?
Yeah, the real world is rarely that accommodating. You cannot always dump unlimited residual cash into a risk-free bank account. Fund managers face strict, inescapable legal boundaries.
Leverage limits, sector caps mandated by their clients.
Exactly. We've built this perfect, unconstrained mathematical engine, but a real-world fund manager can't just borrow infinite money. They have legal limits. So how do we force this pristine calculus to respect the law?
This introduces us to the method of Lagrange.
You know-
Yes. Joseph Louis Lagrange was an 18th century mathematician, and his method is the absolute hero of constrained optimization in quantitative finance. Lagrange developed a way to deal with equality constraints.
Equality constraints, meaning situations where a specific condition must be exactly met, no exceptions.
Right. The text introduces the Lagrangian function. It takes the original objective function you want to maximize, and it adds the constraint functions to it, but multiplied by a new variable called a Lagrange multiplier.
Okay, to visualize this for the listener, imagine you were trying to run the fastest possible route through a massive city park. Maximizing your speed is your objective function.
Okay, I'm with you.
But the park authorities have given you a strict equality constraint. You must stay exactly on the paved paths.
Which is super annoying if you're trying to set a record. In standard calculus, figuring out the absolute fastest route while strictly mathematically binding your coordinates to a winding path is a total nightmare.
So Lagrange introduces this multiplier, which acts almost like an infinitely strict referee running right behind you with a whistle.
A referee with a whistle. That's good.
The Lagrangian function basically says, go ahead, treat this like an unconstrained problem. Run wherever you want through the park, across the grass, through the flower beds.
Sounds fun.
But say the moment one toe touches the grass, violating the constraint, the referee blows the whistle and applies a massive mathematical penalty to your time.
The mechanism here is what makes it beautiful. You take the derivative of this new combined Lagrangian function and set it to 0.
Right.
By doing this, you are forcing the math to find the exact point where the pull of wanting more return is perfectly counterbalanced by the push of the mathematical penalty from violating the boundary.
So if you perfectly obey the constraint, the penalty term zeroes out and your objective function is untouched. If you deviate, the penalty forces you back.
It effectively transforms an impossible constraint problem back into a solvable unconstrained optimization problem. You take the partial derivatives with respect to your assets, and with respect to the new referee multiplier, set them all to 0 and solve the system of equations.
And when you take the derivative with respect to the Lagrange multiplier, you actually recover your exact original constraint equation, don't you?
You do. It is a perfectly closed mathematical loop. You check your Hessian to ensure curvature, and you have found the optimal constrained solution.
Man, math is cool. Now that we understand the tools, how to find gradients, how to penalize risk with lambda, and how to force the math to respect boundaries with Lagrange multipliers, we can apply it to the ultimate goal.
Constructing the portfolio opportunity set.
The text note's an interesting convention here, actually. Portfolio selection is generally defined as minimizing risk subject to a return constraint.
Right.
Instead of trying to maximize return for a given level of risk, the industry standard flips it. Why is that? Why mandate a specific return and then minimize the risk?
It really comes down to human psychology and institutional liabilities. Intuitively, it is vastly easier for an investor or a massive institution to articulate a concrete return objective than a vague risk objective.
Give me an example.
Well, a pension fund manager can easily look at their actuarial tables and say, I mathematically require an 8% annualized return to meet my obligations to retirees in 20 years.
So that 8% becomes a hard, non-negotiable constraint.
Exactly. It is incredibly difficult, however, to answer the question, exactly how much daily variance are you willing to tolerate in your equity curves?
Yet nobody knows how to answer that until they're actively losing money.
Right. So by setting the return as the hard constraint, we allow the Lagrange multipliers to find the absolute safest, lowest variance path to hit that necessary 8% target.
The visual representation of this is iconic in finance. If you plot every single possible combination of risky assets on a graph, with risk on the horizontal axis and return on the vertical axis, it forms a massive, solid, bullet-shaped blob pointing toward the left.
That blob represents the opportunity set.
Right. But you don't want your portfolio to be lost inside the middle of that blob. You want to be on the absolute top left edge of it.
Because that's where the best returns are for the lowest risk.
Exactly. That razor-thin boundary is the efficient frontier. For any specific level of risk you take, that frontier guarantees you are getting the absolute mathematical maximum return possible.
And we use the method of Lagrange to pinpoint the most vital portfolios on that frontier. The most obvious is the minimum variance portfolio.
Which is where on the blob?
This is the absolute tip of the bullet, the point furthest to the left on the graph. It is the portfolio of risky assets that possesses the lowest possible volatility, completely regardless of its expected return.
So just the safest possible mix.
Right. To find it, the optimization engine minimizes the portfolio variance, subject to the strict equality constraint that the portfolio weights must sum exactly to 100%.
And as you move up and out from that tip, along the efficient frontier, you find something even more important, the tangency portfolio.
The tangency portfolio represents the absolute best combination of risky assets you can possibly hold before you introduce the risk-free bank account into the mix.
How do you find it on the graph?
If you draw a straight line originating from the risk-free rate on the vertical axis and angle it so that it perfectly grazes the curved upper edge of the bullet-shaped opportunity set, the exact point of contact is the tangency portfolio.
Ah, so it represents the maximum Sharpe ratio, the highest possible excess return per unit of risk.
Exactly. And the source material grounds this with a concrete numerical example. It simulates a 4-asset market and runs the optimization. The math spits out the tangency portfolio allocation with stunning precision.
What are the numbers?
It dictates weights of roughly 71.2% in Asset 1, 6.5% in Asset 2, 12.4% in Asset 3, and 9.7% in Asset 4.
So precise.
Very. It claims this exact specific blend will yield an expected return of roughly 8.5% with a standard deviation of 12.8%.
But, I mean, here's where that theoretical elegance collides violently with reality.
Oh, absolutely.
We have these incredibly precise weights, 71.2%. But if all of the inputs, the expected returns, the massive covariance matrix, are based entirely on historical data, aren't we essentially driving a race car down a winding highway while staring exclusively in the rearview mirror?
That is the perfect way to put it.
Like, if inflation spikes unexpectedly tomorrow, or a geopolitical conflict erupts, the historical covariance between sovereign bonds and tech equities breaks down instantly. Doesn't this perfectly executed math just create a perfectly wrong portfolio if the future doesn't look exactly like the past?
That critique is the Achilles heel of traditional quantitative finance. Unconstrained or historically constrained mean variance optimization is notoriously hypersensitive to its inputs.
Meaning it overreacts to the data you feed it.
Massively. If you feed the Markovits engine historical data that includes a lucky 5-year bull run for a specific sector, the algorithm behaves like a naive machine. It assumes that historical anomaly is an eternal physical law.
So it'll just dump all your money into whatever did well recently.
Exactly. It will output highly concentrated, wildly unrealistic portfolios. It might suggest you put 90% of your multi-billion-dollar fund into a single tech stock simply because its historical Sharpe ratio was mathematically dominant.
Which is insane.
Right. The engine lacks common sense. It lacks human context.
Which brings us to the most fascinating and arguably most important part of the source material, the Black-Litterman model.
The holy grail of portfolio optimization.
This is where the industry finally figured out how to inject human intuition back into the cold, historical math.
To understand the gravity of this, imagine the scene at a massive firm like Goldman Sachs in the early 90s.
Okay, picture.
On one floor, you have brilliant quantitative analysts running massive covariance matrices through supercomputers, generating these mathematically perfect, backward-looking Markovits portfolios.
Right. The quant's staring in the rearview mirror.
But a few floors down, you have an army of fundamental analysts. These are people visiting factories, analyzing supply chain bottlenecks, reading the geopolitical tea leaves.
The boots on the ground.
Exactly. And they are generating highly informed, forward-looking views on where the market is actually going.
But the quants and the fundamental analysts were speaking entirely different languages, weren't they?
Completely different. The quant has a matrix of second derivatives. The fundamental analyst has a well-researched thesis that European manufacturing will outperform U.S. manufacturing by 2% over the next 3 quarters.
So how do you bridge that gap? How do you mathematically harness the human analyst's foresight to correct the quant's backward-looking algorithm?
Fisher Black and Robert Litterman solved this exact translation problem, and their solution bypasses standard calculus entirely, relying instead on Bayesian statistics.
Bayes' formula.
Right. The core philosophy of Bayes is that you start with a prior belief, a baseline expectation.
Yeah.
Then, as new evidence or information arrives, you mathematically update that prior belief to form a new, superior posterior expectation.
It operates as a rigorous, step-by-step roadmap for institutional capital. Step 1 is establishing the prior. You can't just start with a blank slate.
No, you need an anchor.
But you also can't start with historical data, because we just established that historical data creates concentrated, naive portfolios. So Black and Litterman chose the equilibrium CAPM portfolio as their foundational prior.
It is a stroke of structural genius. By starting with the CAPM equilibrium, they assume that in the absence of any special proprietary human insight, the broad market is generally efficient.
So the global market capitalization weighted portfolio serves as the baseline.
Exactly. It assumes excess returns are normally distributed around this massive, stable equilibrium. This anchors the mathematics. It prevents the optimizer from doing anything wild or concentrated before you even begin the process.
And then comes step 2. Inputting the views. This is the moment the fundamental analysts get to speak directly to the algorithm.
And the Black-Litterman model accommodates 2 distinct types of human views. First, you have relative views.
Give me an example of a relative view.
An analyst might come upstairs and say, based on my research, I believe asset 3 will outperform asset 1 by exactly 10% over the next year.
Okay, so it's a comparison.
Right. The model translates this relative view mathematically into a matrix called the P matrix, representing it as a synthetic long-short spread trade. It assigns a positive 1 weighting to asset 3 and a negative 1 weighting to asset 1.
And the second type is an absolute view. An analyst might simply state, I believe asset 2 is going to return exactly 3%.
Right, which is represented as a straightforward long position. But the real genius of the model isn't just taking the view, it's demanding a level of certainty.
The confidence interval.
Yes. The analyst cannot just throw out a guess. They must attach a mathematical confidence level to their view, denoted by the variable omega. How absolutely sure are you that European manufacturing will outperform?
This is where the Bayesian synthesis occurs, right? The Black-Litterman formula takes the massive, stable CAPM prior portfolio. It takes the matrix of subjective human views, and it weights them against each other based on the volatility of the assets and these stated human confidence levels.
Exactly. If the analyst is supremely confident, the math physically pulls the final portfolio weights away from the safe market cap baseline and heavily tilts toward the analyst's thesis.
But if the analyst is uncertain, indicating a high variance in their own prediction, the model largely ignores the view and stays safely anchored to the baseline.
The source material provides a numerical example that exposes the wild, almost terrifying impact of this confidence interaction. We are revisiting our lambda, our fear dial, but now we are looking at how it interacts with human confidence in a Bayesian framework.
The math is astonishingly sensitive to these subjective dials, isn't it?
It really is. Consider the extreme scenario laid out in the text. Imagine the risk aversion lambda is set to zero point 0.1.
A very low fear dial.
With the analyst's subjective views injected into the engine, the optimal weights the Black-Litterman model outputs are completely unhinged.
Unhinged how?
It demands putting 898.5% of your portfolio weight into a single asset.
Wait, what? 800%?
Yes. To physically achieve that, the math dictates you must borrow 1,614% of your total net worth at the risk-free rate, applying massive leverage to express this one specific human opinion.
Which is, of course, a fast track to institutional bankruptcy, if the analyst is wrong.
Oh, without a doubt. Even when the text dials lambda up to 1, which represents a more normal, though still highly aggressive risk appetite, the model outputs an 89.85% weight in one asset, requiring the fund to borrow 71% at the risk-free rate.
And the author dryly notes this is still not for the faint-hearted.
An understatement.
And if we look at the other extreme, if you crank the fear dial up to a lambda of 6, the model becomes utterly terrified of the human views.
The risk penalty is so high that it overrides the potential alpha.
Right. It instructs the manager to put 71.43% of the entire portfolio safely into cash, into the risk-free rate, barely touching the risky assets, despite the analyst's research.
It's a huge swing.
This is where I have to push back on the entire premise of what we are doing here. We have spent this deep dive exploring an incredibly complex, Nobel Prize-winning mathematical architecture. We've discussed matrices, gradients, Lagrange multipliers, and Bayesian updating.
All very rigorous.
But at the end of the day, the final output of this flawless engine can swing wildly from hide 71% of our billions in cash to borrow 16 times our net worth and bet it all on black. And that catastrophic swing is entirely dictated by a subjective confidence dial set by a human analyst.
It's wild when you frame it that way.
Doesn't that entirely defeat the purpose of quantitative objective optimization? Are we just laundering human opinion through complex math?
It is the ultimate paradox of modern quantitative finance, honestly. The mathematics are structurally perfect, the optimization algorithms execute flawlessly, but the inputs will forever be tethered to the inescapable uncertainty of the future and the reality of human bias.
So it doesn't fix human error.
No, the Black-Litterman model does not and cannot eliminate human error. What it does is provide a mathematically rigorous framework for translating that unavoidable human bias into actionable, risk-managed portfolio weights.
Oh, I see.
It ensures that if an institution chooses to believe their analyst is right, the resulting portfolio is the absolute most efficient, geometrically sound way to express that specific belief without accidentally blowing up their risk profile through unintended correlations.
It is fundamentally risk management for human opinions.
Exactly. It manages the fallout of our own beliefs.
Which is a perfect segue into the very last bit of reality the text introduces. We talked about Lagrange handling equality constraints, the referee blowing the whistle the moment you step off the exact paved path.
Right.
But the real world is governed by inequalities, isn't it?
Yes, the primary limitation of the method of Lagrange is that it only handles strict equations. But the most common constraint in global finance is the no short selling rule.
Meaning what?
Most mutual funds and pension funds are legally prohibited from shorting stocks. This means every single asset weight in the portfolio must be greater than or equal to 0.
And Lagrange cannot process a greater than or equal to sign.
Nope. To handle this, the quantitative world turns to the Kuhn-Tucker conditions.
The Kuhn-Tucker conditions?
Yeah, they are an evolution of Lagrange. The mathematics introduce additional specialized multipliers specifically designed to handle these inequality boundaries.
So back to our park analogy.
Right, in our park analogy, the referee doesn't just blow the whistle if you step off the path. They also blow the whistle if you try to run backward. It introduces directional constraints.
But there's a catch. Right.
Always a catch. The text includes a vital caveat regarding Kuhn-Tucker. It only guarantees you have found the true optimal solution if your objective function is strictly convex, meaning perfectly shaped like a bowl, and if your constraints are linear, straight line.
And if they aren't?
If the mathematical landscape is too warped or complex, the Kuhn-Tucker algorithm might get stuck on a false ledge, mistaking a local minimum for the global valley.
So you think you've hit the bottom of the canyon, but you're just on a cliff ledge.
Back to the darkness of the mountain range.
You know, if you're listening to this and wondering why on earth you should care about the convexity of a Kuhn-Tucker condition or the Bayesian priors of Goldman Sachs quant, especially if you aren't managing a billion-dollar hedge fund, it's because optimization is not just about stocks.
It really isn't.
It is the fundamental architecture of human choice. Every single time you sit down at your desk and attempt to maximize your career output while managing the strict inequality constraint of a 24-hour day, you're actively running a complex optimization problem.
That's a great point.
When you are agonizing over the expected return of taking a risky career jump to an unproven startup and weighing it against the variance of leaving your current, safe, predictable job, you are literally performing mean variance optimization in your head.
You're trying to figure out your own lambda.
Exactly. You are intuitively weighing your personal fear dial, your internal lambda, against the historical covariance of your industry. The complex mathematics we explore today, the gradients, the constraints, the Bayesian updating of beliefs, it is simply a formalized, rigorous language for the difficult trade-offs you navigate every single day.
And that is why this material is so enduring. What the quants have achieved is stripping away the raw emotion of decision-making to reveal the geometric truth of trade-offs.
Yeah, the geometric truth. I like that.
They have mathematically proven that risk and return are inextricably tethered by covariance. They have shown that constraints physically alter the shape of what is possible, and they have demonstrated through Black Litterman that even the most rigorous, flawless mathematics must eventually reckon with the deep uncertainty of the future.
Which leaves us with a lingering thought to consider, building directly on that Black Litterman model. We just saw how a subjective human view and a human's internal confidence level can drastically alter the output of a perfect mathematical engine, shifting billions of dollars based on a gut feeling about European manufacturing.
Right.
But we are standing on the precipice of a fundamentally new era. What happens to the global financial system when an artificial intelligence, rather than a human analyst, begins providing those absolute and relative views to the optimization algorithms?
Oh, man. That changes everything.
Right. If an AI system autonomously analyzes satellite imagery of every shipping port on Earth, parses every corporate earnings call in real time, and feeds a relative view into a Black Litterman engine with a mathematically calculated confidence level of 99.9%.
The math will just run with it.
The optimization math is going to allocate capital with a speed, scale, and concentration that human risk managers have never dared to attempt. Are we actually using these models to eliminate risk from the markets? Or are we just building incredibly complex, mathematically flawless equations to eventually validate an entirely new, non-human scale of overconfidence?
That is a terrifying thought to end on.
Think about that the next time you try to find the lowest valley in the dark. Thanks for joining us on this deep dive.